Learning Outcome 10-12. Draw block diagrams for discrete systems using delay units. In Chapter 8, we did a review of block diagram elements, particularly convolution, addition, and the gain block. We're going to use these here. The convolution block, you now need to note, has discrete elements to it. And the transform is no longer the Fourier transform, it's the Z transform. Although similarly, convolution in time becomes multiplication in the Z domain. Addition stays the same, except for we have discrete time, and our transform is in the Z domain. Linearity still holds. Gain is similar, again discrete time, the Z transform, and linearity still holds. Within the convolution block, and the part I want to focus on here is not for a generic h of n, h of z, but for the z to the negative 1, which is a time delay block, which is used considerably in discrete systems. When our h block becomes z to the negative 1, we usually put the z to the negative 1 first, and the inverse transform of our z to the negative 1 is a unit impulse shifted by 1. By using the shifting theorem, that's going to be our x variable delayed by 1 unit. So our y of n really is just going to be a delayed x. And this transformation of x of n to a delayed x is why these are called delay units, and are the key to the block diagrams we use considerably in Chapter 10. So let's work out 3 examples. We'll start off with y of n equals x of n plus 2x of n minus 1. Our source is x of n, which has the transform x of z. We can put that through a delay block, and out will come x of n minus 1, and the z transform is z to the negative 1 x of z. We're trying to form y of n, which means that we need to have x of n and 2 of our delayed x's. So we need to have x of n as one of our elements, and we need to have our x of n minus 1 scaled by 2. These are joined with a summation, and that forms our output y of n. The next example is more characteristic for Chapter 10, block diagrams with delay units, and requires a little bit of nuance to see the trick of how we do this. You need to remember that our source is x of n. Our source will always be x of n because x is our input. Our output will be y of n. Y of n is always our output. But this time we're not delaying x, we're doing a delay on y. So we will tap this line and add a delay to that. What comes out of the delay is our delayed y. Now comes the trick. We want to rewrite our equation to solve for y of n. How do we build our output from the things which we have available to us in our diagram? Well, there's our x. There's our y of n minus 1. We need to have negative 2 of those y's. So we put it through a gain block, and that output we're going to add together with our x of n to produce our y of n. This is it. We're done. This is a second order system where we want to apply the same trick. X of n is our source, y of n is our output. Because we need a y of n minus 1, we put a delay on y of n, and that gives us our y of n minus 1. But look, we also need a y of n minus 2. So we can delay that again, and that gives us our y of n minus 2. And we reroute the output of that first delay. This is just a way of making things look pretty. Now we have all the elements here. We have our x of n, we have our y of n minus 1, we have our y of n minus 2. We need to add the appropriate gains and then sum them. The gain for y of n minus 1 is negative 2. The gain for y of n minus 2 is negative 3. We add them, and that forms our y of n. I mostly want you to be familiar that these things exist. We're not going to use them extensively this semester, but this is something you need to be aware of and have some idea how to do this for when you will need it in a future semester and in your career. We call this a tap delay line because we have all these delays and we're tapping the outputs of them to provide the input to form our equation. There's some nuances involved if we're going to delay x as well as delaying y. I'm not going to get into those here. Mostly I want you to be aware of what these delay blocks are. And if you ever see a block diagram, start labeling the wires. And as you start labeling the wires, you can start writing equations around every summation. And then you'll know what the equation is.